In this video, we're going to go over section 10.2 class node problems. So in here, we're going to go with graphs, and we're going to translate those graphs to adjacency matrix. So let's go with question number 1. We have this graph here, and so we have 4 nodes that are interacting among each other. And the way that we're going to fill this matrix, this adjacency matrix, is if we have one node that has an edge going towards another node, then we're going to have that there's a 1. If there's not a node going from that node to another particular node, then we set a 0. So for example, B1, we look for the row for B1. And so from B1 to itself, there is nothing. So we're going to put 0 here. From B1 to B2, there is one edge going. So we're going to put 1 here. From B1 to B3, there's also 1 here. And from B1 to B4, there's nothing. So we're going to get 0. Now from B2, we only have 1 node going to B4. And so we're going to put a 1 here. And everything else is going to be full of zeros. From B3, we have multiple things. Notice B3 is going to B1, so we're going to have a 1 here. B3 is also going to B4, so we're going to have a 1 here. And B1 doesn't go to B2 and doesn't go to itself, so we're going to have zeros here. And now last, B4 doesn't go anywhere, but just to itself. It has an edge that is going to itself. So it's going to have a 1 here, and we have 0 for everything else. All right. So now let's go and that is for adjacency matrix, and this is for directed graph. Now for undirected graph, we have a similar situation, but now we're just gonna consider if we have an edge between 2 of the particular node. All right. So for example, A doesn't have a node that goes to itself, but it has a node that goes to D, to V, and to E. So we're gonna put a 1 in here, 0 in here. It doesn't go to C, but it does go to D and to E. From B goes to A. B doesn't go to itself. B goes to C. B doesn't go to D, but B goes to E. Now for C goes to B and C goes to E. So C and E, and we don't have anything else. Sorry, to B. So not to C. Goes to B and to E. Okay, now for D. D is going to A and is going to E. So we have a 1 here, and we have a 1 here, and we don't have anything else here. Oh, but also notice that we have 2 nodes from D to E. So we're not really going to use 1. We have 2. So we're going to do a 2 here. We have 0, 0, and 0. Now, from E, E goes to A, goes to B, goes to C. So we have 1, 1, 1 here. To D has 2. And to itself, it has nothing. So that's pretty much what we have here. Now we're checking for degrees. Remember, degrees is how many incident edges a node has. So for example, A has 3 edges, so it's degree 3. B has 1, 2, 3, so degree 3. C has 2. D has 1, 2, 3. And E has 1, 2, 3, 4, 5. All right. Okay. So now question 3. So for question 3, we want to do the opposite. We have an adjacency matrix, and we want to write an undirected graph that connects all those vertices. So we have the connection here. We're going to assume that this is B1. And so B1 is not connected to itself, but it's connected with B2 with two different edges. So B1 connected to B2. Now B1 is connected to B3. So we're going to have to do this. And B1 is not connected to anything else. Now B2 is connected to B1 by 2. So the same edges here. Is not connected to B3, it's not connected to B2, but it is connected to B4. So we do this. Now B3. B3 is connected to B1, we have it here. It's not connected to B2. It is connected to B3, so we're going to have one with itself. And it's connected to B4. So we have this situation here. Now B4 is not connected to B1. It's connected to B2, which we already have. It is connected to B3, and it's not connected to itself. So this is going to be the graph that represents this matrix. Now let's go to question number 4. Question number 4 is, what is... here we want to tell what is the entry A33 tells you about the graph before I forget. So the A33 is this, and what this says is that it has an edge connected to itself. So before I move on to the next one. So that's what the A33 equals 1 means. Now for question number 4, we want to compute the following matrix products. And so what you got to remember is that when we're doing matrix multiplication, then we're doing an entire column by a row. So for example, the first entry is going to be this this column by this row. So it's going to be 4 times 1 plus minus 1 times 2. And that's going to be the first entry. Then the second entry below is 4 times 3 plus 0 times minus 1. Or minus 1 times 0, which is the same. This is the first column of my new matrix. And now we're going to have the second one, which is going to be 1, 2 multiplied by 1, 2. So this is going to be 1 times 1 plus 2 times 2. And then we're going to have 1 times 3 plus 2 times 0. Then we add all these results, and that's going to give me my matrix product. This is going to be 4 minus 2 is going to be 2. It's going to be 12. Here we have 1 plus 4, so it's going to be 5. And this is 3, since 2 times 0 is 0. Okay, and that's my new matrix in here. Now, when we have a square, the situation here is I just have the matrix by itself. You gotta remember that. So this is the matrix by itself. And so now I'm gonna do the multiplication more quicker. This row by this column, this is gonna be 0 times 1, 1. It's gonna be 2 here. 0 times 0, 1, 1 times 1, 0, 1 is just gonna be 1. 0 by this is just going to be 1. 0, 1, 1 by 1, 1, 0. Now we do 1, 0, 1 by this. And so notice that that's going to be just 1. This one is just going to be 2. And the last one, 1, 0, 1 times this is just going to be 1 once again. Then 1, 1, 0 multiplied by this is just going to give me a 1. 1, 1, 0 by this is giving me 1, 2. And finally, 1, 1, 0 times 1, 1, 0 is just going to give me 2. So this is my matrix square. This is the result of that. All right, moving on. Let's go to question 5. All right, so let's compute A times B. So if we do A times B, we're having 1, 0, 2, 1, and 0, 1, 1, 0. And this is just going to be 0 here, and it's going to be 1 here, 1 here, and it's going to be 2 here. This is AB. Now we compute BA, that's going to be backwards, so 0, 1, 1, 0 times 1, 0 to 1. And matrix multiplication, notice that this is going to give me 2 here. 1 times 0 plus 1 times 2 is going to give me 2. 1 times 1 plus 2 times 0 is going to give me 1 here. 0 times 0, 1 times 1 gives me 1 here. And 0 times 1, 0. 1 times 0, 0. So it gives me this. So the questions he asked, what does this illustrate about matrix multiplication? Well, this pretty much illustrates that A times B is going to be different from B times A. And so multiplication of matrices is not commutative. And that's important because that tells me information about how matrices are going to behave and how corresponding graphs might behave. So talking about corresponding graphs with their matrices, let's consider this adjacency matrix. And so, by the way, this is 4 nodes. I'm gonna put 4 nodes in here, and I'm just gonna really quickly draw the graph so we can use this for visual purposes later. So this tells me that B1, let's call this 1, 2, 3, and 4. So this is telling me the node 1 is connected to the node 2 and the node 3. For the second one, it tells me that the node 2 is connected to 1, is connected to 3, and to 4. So we have this situation. From node number 3, it tells me that it's connected to 1, to 2, and to 4. So node 3 is connected to 1, to 2, and to 4. So we have this situation. Now from node 4, it tells me that it's connected to node 2 and node 3. So this is my graph. Now says without computing, list all the walks of length 2 to be from B1 to B1. So pretty much I want to do a walk where I take a walk from B1 or node 1, go to another node, and come back. That's a node of length 2. So in this case, those nodes are going to be what? Those nodes are going to be from B1, I go to B2, and from B2, I return to B1. And you can see it here. From 1, I go to 2, and then return to 1. And the other option is, of course, from 1, I go to node 3, and from node 3, I go to back to B1. That's all the possibilities. And so the count here is 2. We have 2 walks in there. Now, the purpose of the powers here is that going to give me all the walks that match that with the A square matrix. So if I do A square, notice that I'm going to have the following matrix. It's going to be 2, 1, 1, 2, 1, 3, 2, 1, 1, 2, 3, 1, and 2, 1, 1, 2. You can verify that by matrix multiplication of this matrix by itself. Notice that A squared 1, 1 is giving me 2. And so that matches the number of walks that I'm doing from the node 1 to the node 1, and it's 2. Now, if I want to determine how many walks of length 2 exists from B1 to B4, I'm going to use the matrix A squared because these are walks of length 2. And because I want to do from 1 to 4, then I'm going to do the entries A1, 4. And so the entry A1, 4, you can see it here, is 2. And so this tells me that it says 2 walks of length 2 from B1 to B4, which is pretty much what? From B1, I go to B2, I go to B4. And now from 1, I go to 3, and I go to 4. So those are the 2 walks of length 2. B1, B2 to B4, and B1 to B3 to B4. So it helps me to see if I have the graph actually from the matrix. It helps me to see how many walks are possible. All right, so now let's go to question 7. So it says, using the matrix from the problem 6, so we're using this, we want to compute a tree. And so we want to see what are the matrices, what are the walks of length 3 from B2 to B2. So we're pretty much gonna take the same matrix here, and I'm gonna multiply by this, and I'm gonna get a cube. Okay, and so if I get a cube here, I'm gonna get that this is 2, 5, 5, 2, 5, 4, and then 5, 5. If I multiply, and then 5, 5, 4, 5, and 2, 5, 5, 2. Please verify, just compute, please compute a squared times a. Particularly, you should be computing this times this, and you should have this result. Okay? So now you want to walk of length 3, which we're using a cube, right? And so we're using a cube. That's go from B2 to B2, and that passes through 4. So we have a tree from B2 to B2. We have 4 walks, right? But we have a second condition, and is we have that passes through B4, okay? And so we want to identify that. So we can kind of list those walks. Essentially, the graph is still going to be the same. And so there are walks of length 3 that goes from B2 to B2, so B2 to itself. And so I can go and check those. So for example, we have from B2 go to B1, go to B3, and then come back to B2. This is one walk. We're doing from here to here to here, and then back to here. Okay, number 2, another walk. Is going to be from B2, go to B3, go to B1, and then go to B2. Once again, notice from B2, we're going to B3, and then going to B1, and then going to B2. We're doing this circuit here. From 3, we can do another walk where we're going through 4. Now, from B2, go to B3, go to B4, and then go to B2. So from here, go to here, go to here, go to here. So that passes through B4, we already have 1 at least. Let's go one more walk that we have pending. We can go from B2 to B4, and then we can come back to B3, and then from B3 we can go to B2. So it's going backwards here. From B2, go to B4, go to B3, come back. So we have another one that goes through 4. All right, so that's enough for part 1. Let's continue this in part 2.